Hello everybody. So today we are discussing a new topic, linear momentum. Momentum is a very important concept in physics, widely used, so many applications, not just in physics but in biology, chemistry and other scientific fields. Whenever there's motion is involved, motion of objects, motion of masses or particles, momentum can be a very powerful tool to study the behavior. Excuse me. So these are the topics. We'll talk about what is momentum and how momentum and force is related. Momentum conservation. We talk about, we have discussed energy conservation. So similar to, there is a conservation concept for momentum as well. And a few more topics, some keywords like impulse, and then collisions between masses. Collisions are especially important when it comes to molecular sciences, so chemistry, where particles collide with each other all the time. So momentum is a great way to study these collisions and to understand the outcomes of these collisions. So we're gonna briefly discuss about all these important topics. Okay. Alright, so let's see what momentum is. Okay, momentum. It's a property of moving objects. If a mass is moving, let's say here's some mass. It has a m kilograms. This is moving with the velocity v. Momentum is defined as mass times velocity. Pretty simple, mv. We use the capital letter P, actually small letter P, it shouldn't be the big one, letter P to indicate momentum. So P equals mv. Couple of things to remember. Momentum is a vector. So momentum has a magnitude and direction. So we have to say this much momentum in the x direction or this much momentum in the y direction, like that. The measuring unit, momentum is measured by, now if you think about mass is in kilograms, velocity is in meters per second, so momentum is mass times velocity, therefore it's kilograms meters per second. This is the unit of momentum. Okay. As I said, it's very straightforward. It's a property of moving objects. If a mass is moving, it has momentum. It's kind of like kinetic energy, right? It's half mv squared. It's a property of moving object. One main difference between momentum and kinetic energy is momentum is a vector. It has the direction is important. Kinetic energy doesn't have a direction. It's a scalar. All right. So let's think about a quick example. Let's say some particle has, some object has mass of 10 kilograms, moving with a speed of 20 meters per second. Momentum is mv, therefore 10 times 20 kilograms meters per second. This is how you find momentum. Pretty simple thing to calculate, but very important in understanding systems, moving systems. You wouldn't see the real power of momentum in this class because we're going to study examples like moving vehicles, momentum of people and certain like macroscopic large scale objects, but it's very, very important if you study behavior of molecules, motion of gas particles, small scale microscopic stuff. That's where the real power of momentum is in. Okay, all right, but we'll look into a couple of examples. Okay, so let me erase this and start a new page. Okay, so now you know how to find momentum. Simply momentum is mass times velocity. Now let's see how momentum is related to force. There's a simple relationship between momentum and force. Think about this equation, P equals mv. If I divide both sides by time, right, divide by time, mv divide by time, I can write this as, I can take m out and velocity over time. Now if you think about a velocity difference, like normally imagine something's moving with some velocity, a vehicle moving, and you apply a force on it, like you press the gas pedal and increase the force acting on the vehicle. It accelerates, right? The speed changes. So when you apply a force on a moving object, you can change the velocity. It could be a directional change, it could be the magnitude changes, but you can make a change to the velocity. Usually mass doesn't change, mass remains the same. If it is a moving car, the mass doesn't change, right? So by applying a force, you can change the velocity. So let's assume that there's a velocity change, little delta change, divide by time, and we know that delta v, velocity change divided by time, is acceleration. This side is still momentum divided by time. Now what is this? Mass times acceleration. This is force. So force can be defined as the change in momentum over time. So as I said, force can be defined as the momentum change divided by time. So let me write it over here. F equals change in momentum over time. What does this mean? So as I explained, if we go back to the example of a vehicle has a mass m moving at a velocity v1. You apply some force on it. You press the gas pedal. You apply additional force. Now velocity become v2. What's the initial momentum? mv1. Over here mv2. What's the change in momentum? Delta p. The change is mv2 minus mv1, right? Change is always final minus initial. So here's the change. Now if I divide this change by time, I'm explaining the same thing in a little different way, okay? If I divide this change by time, I have this side also mv2 minus mv1 over time. I can take this m out, velocity difference over time. You know this is acceleration. So delta p over t is mass times acceleration, which is force. So when you apply force, you can change the momentum of something. You can increase the speed, you can decrease the speed. You know that is like when you apply a force, you can create an acceleration. Momentum is another way of explaining the same thing. Alright, so that's that. Using calculus, now this is a algebraic way of explaining this. Using calculus, we can say, now we write F equals dp over time. Using calculus we can say F equals dp over dt, the derivative of momentum in terms of time, right? So here's another way to explain force. Newton's second law says F equals ma. Same thing, Newton's second law, we can explain it using momentum change over time. That's another way of explaining Newton's second law. Okay, all right, so let's look at few examples of how momentum and force related. We will try few. So let me clear this. All right, so let's take a look at an example related to sports, playing tennis. So it says that again I'm using these examples from the PowerPoint, which is under files. The example says a tennis player, so when you serve the ball, just hitting it to serve it to the other side. So the tennis ball, like normally how you do it is, I'm not a tennis player to explain too much, but you kind of throw it up, right? And then here's the tennis racket. You bring it fast towards the tennis ball. So the tennis ball and the racket are in contact with each other for a brief moment, right? It's still moving, and then ball is going to leave with some high velocity, right? So the ball is initially at rest, right? It didn't have any horizontal velocity. It was v was 0. Still v is 0, but now right after there's a contact between the racket and the tennis ball, it's going to accelerate. Now it's it'll start moving forward with the racket, right? So but it's starting from 0, but it's accelerating. After some distance moving together, now the ball has this final high velocity and it's gonna continue going forward. Okay, now let's say we are interested in calculating the force involved in this process. What's the force? Because these things are important if you're playing tennis, if you're a tennis coach, or if you're a doctor or a physiotherapist dealing with somebody having injuries due to playing these sports. If you're somebody doing research to improve the science of these sports activities. So knowing the force involved, the impact and all that is pretty important. One way to do this is, if we can calculate the acceleration of the ball during this contact time. It accelerates only during the contact period. It's like a couple of milliseconds, right? After that, it's going to leave with this final velocity. If you find the contact time, if you can measure the time, if you can measure the acceleration, if you can measure v final, or if you can measure the distance it accelerates while it's in contact, these things, then we can find force. We can, so using kinematic equations, we can also use momentum concepts to do the same thing. Okay, so let's see what data we have. It says that the ball starts from 0. It leaves with a speed of 55 meters per second. That is for like a top level player. This is kind of equivalent to 120 miles per hour, so that's pretty fast. Mass of the ball is 0.06 kilograms. That's standard for a tennis ball. And it's in contact. it's in contact with the racket for a time interval of 4 milliseconds. Now usually, no, never mind. Okay, now the question is, estimate the average force on the ball. How much force we are applying. We can use kinematic equations, but let's see how to do this with how to solve this using moment. Okay, so for this particular problem, since we have pretty much all the information we need, I'm gonna directly start with F equals delta P over T. Now this is actually same thing as using kinematic equations, using Newton's second law, all that, but it's kind of, this expression over here combines all of these things into one equation, so that's the advantage here. Okay, so delta P over T, momentum change divided by time. So what's the change in momentum? Initially, the moment the contact happened, this is our initial state, right? P initial. Just before losing the contact, right? Now forget this, it's just before losing contact, like just like a moment right after losing contact. Now the ball has its final velocity. This is our final state. So P final minus P initial over time. Delta P, the change, final momentum minus initial momentum gives you the change divided by time. Now what is P final? This is the tennis ball, the mass of it, and velocity final. P initial, mass of it, velocity initial, divided by time. That is the force. Now we can plug numbers. I can even take this M out and put a bracket here. That's even easier. V final, V initial over T. You see that this is again the familiar acceleration term. So force equals 0.06, 55 over minus 0 over 4 milliseconds is 0.004. Okay, alright, let's see what the force is. You guys gonna need the calculator. I get 825 newtons. That's a pretty big force, 825 newtons. Imagine, so this is the force a good tennis player would apply when they serve the tennis ball, right? You can, let's say, like for a comparison, if I divide this number, this is just a comparison, by gravity 9.81, this is kinda equivalent to a lifting force of 84 kilograms. 84 kilograms is a grown-up person. This serve, the force behind this serve is enough to lift such a big person, right? So that's a lot of force. Anyhow, this is how you calculate the force using this momentum relationship. This is an example of how force and momentum are related. So the important piece here is this equation. Okay, let's move on. Okay, so I told you that we're going to talk about momentum conservation, or conservation of momentum. Now this is the most important, most powerful aspect of momentum. In a system of moving objects, you can think of a system of gas particles, right? There's gas molecules, let's say oxygen gas. There's molecules moving around in so many random directions. There's millions of collisions occur between them. So to study, if somebody wants to study the outcome of these collisions, like how much energy they lose or which directions they bounce off of each other, so those kind of things, momentum is a pretty powerful tool. So we're gonna look at collisions between particles in particular. So let's think about a system where we have two masses, mass 1 and okay, let's call them mass 1 and mass 2. Let's say they are coming towards each other with the velocity 1 and velocity 2. Okay, so they're coming towards each other. Now they're getting closer and closer and they collide. Here's the collision. Let's say these are two gas molecules, so M1 and M2 colliding with each other, coming in V1 and V2. And after the collision, let's assume that they're going to bounce back. Now we can't say that necessarily they're going to bounce back with the same speed. Could be some speeds. Let's say this is going to go back with V1 dash, V2 dash, right? So during this collision, this is our system. They collide and they bounce back. This is the state before collision, right? Initial. This is the state after collision. They're going in opposite direction. Final. Conservation of momentum says during a collision, the total momentum of the system is a constant. This is kind of like the energy conservation. We talk about the total energy remains the same, not necessarily in a collision, but in a system. Here, these are collisions between two or more particles, right? You have to have more than one in order to have a collision. So you take a system, you measure the initial momentum of that, all the participating particles. Here we have only two, the simplest case. You calculate the momentum of that before collision, and then you calculate the momentum right after the collision. They are equal. The momentum does not change, and that's very helpful to understand what's going on during collisions. This can be applied to small microscopic particles like molecules, atoms, electrons, protons, and all the way to big things, macroscopic things like two vehicles colliding. Law enforcement sometimes use momentum to understand accidents involving vehicles and people and all that. It could be a collision between two football players. Sometimes actually game planners use these momentum ideas to place big players, small players in different places on the ground. So there's so many nice applications like that. So we will look into a couple of examples. So coming back to the point, during a collision, total momentum of the system is a constant. That means what is the final momentum? M1 V1 dash plus M2 V2 dash, which is equals to M1 V1 plus M2 V2. Okay, these are vectors, so when we add, we have to be careful about the direction, but this is what it says: P final is equals to P initial. Okay, That is momentum conservation during a collision. Okay, so let's look into a couple of examples. Alright, so let's think about this situation. Here we have a truck that is 5,000 kilogram going at 20 meters per second, and it's getting closer to a car going at 15 meters per second, has a mass of 1000 kilograms. The truck is bigger, it's coming at a higher speed. Driver is not paying attention, probably he's on the phone. So it's getting closer to the car. At some point there's going to be a collision, and what do you think is going to happen after the collision? Right after the collision, truck might slow down a little bit because of the collision. Car might gain some speed. So we can't have two unknowns, so let's assume that right after the collision the truck's speed drops to, let's say, 18 meters per second. Right, it slows down because of the collision. The car might gain speed. Now the truck lost 2 meters per second. Do you think the car is going to become 17? That it will add up 2 into this? We don't know. We're going to find out. But it will speed up a little bit, right? We are talking about right before the collision and right after the collision. Sometime later things can change. The truck can apply brake or change lane. Car can pull over to a side and call the cops. So many things can happen. This is like just before and just after. That's where we define the system, in that right moment. Because after some time, what happens is frictional forces and things similar things come into play and change the numbers a little bit. So we are not interested in long time effects. Right after collision, what's going to happen? That is our system, just before and just after. Okay, so we're going to write, now this is our final side, this is our initial side. So we can say momentum P final equals P initial. So we have the truck, so mass of the truck, velocity of the truck, plus, right, this system has two moving things. Mass of the car, velocity of the car should equals to the initial number. So okay, I don't need to write all that, so let me get rid of that, this whole thing. So we can say P, come on, momentum final of the truck plus momentum final of the car is equals to momentum initial of the truck plus momentum initial of the car. Now you guys don't have to write all of these, you can directly go into the numbers, but just because this is the first time, I will explain each and every step. So final equals initial, the final momentum is the combination of these. This is the initial momentum, total of these. So momentum final of the truck, mass of the truck multiplied by velocity plus mass of the car, 1000, this is 5000, this is 1000, right, times its velocity, which we don't know, which we are trying to find out, is equals to mass P initial, mass of the truck, times 20 plus 1000 times 15. Now since everything is going in the same direction, and we take this as the positive direction, they're all positive numbers, okay. So the next step is to find out what V is. Now there's a lot of zeros here. I'm going to divide the whole thing by 1000. 1000, this goes away, This goes away. So what do we have? 5 times 18 plus 1 times v, which is v equals 5 times 20 plus 1 times 15. So I'm going to take this to the other side. V equals, I'm going to take 5 out, 20 minus 18. You guys, if you're not familiar with this, just use the calculator. Plus 15, so 2 times 5, 10 plus 15. V equals 25 meters per second. The speed of the car instantly got increased by 10 meters per second, right? It becomes 25. It's quite a shock. So that is momentum conservation during collisions. Now, in few steps, we can find what's the final speed is. The great advantage here is if we are to use kinematic equations, we need to know a lot of things. We need to know the time of impact, like how long they were in contact with each other. We need to measure that time. We need to know how much deceleration or slowing down happened on the truck. It dropped from 20 to 18. We need to know how much acceleration happened on the car. We need to know the forces associated. We need to know the distance traveled during that time they were in contact with each other. So many things we need to measure if we are to use kinematic equations. Doesn't mean they're bad. They're very useful. We need them all the time. But here's a way to bypass all that and come to the final results. If you are not interested in what's going on during the collision, we can use momentum to find what happens right after the collision. Okay. So the truck lost some momentum. You can calculate the momentum change in each individual. The truck had 5,000 times 20. Now it has 5,000 times 18. The amount it lost, the missing piece is what goes into the car. Okay. Alright, so let's take a look at another example. Okay, so here's another example. Let's say we have two railroad cars. One is moving at 10 meters per second, going towards the second one, which is in the front, which is stationary, it's at rest. They both have the same masses, 5,000 kilograms. So this is coming towards the stationary one, and it's going to collide. And after the collision, let's say the two cars get locked to each other, and they're going to move as a single entity. Right now they get locked. This is something they do actually to connect railroad cars one to the other. So the question is, what is the velocity after the collision of this combined system? So here again we can use momentum conservation. We can define this as P final, this as P initial, and we know that P final equals P initial. Final momentum. Now these two cars, we have to treat them as a single unit, right? So each has 5,000 kilograms. As a single unit, you can add them together because they both have the same velocity. You can just add them together. 10,000 kilograms with the velocity of v, that's the final momentum, equals to initial. This is cart number 1, cart number 2. Cart number 1 has 5,000 times 10 plus cart number 2 5,000 times 0, which is 0. Okay, so then what is velocity? 3 zeros cancels out, 1 zero cancels out. I have v equals 5 meters per second. Combined system is going to move with this speed. And if there is no friction on the tracks, it will continue with the same speed. Okay? Alright.